Stuart today for our distinguished speaker series. I can tell he's distinguished because his academics barely fit on this page that I printed out. So he's currently the Bren Professor of Computing and Mathematical Science at Caltech. Before that, he was at Warwick for a while. Before that, he was at this great institution here. Won numerous awards in applied math, including the Leslie Fox Prize, the Martin Prize, the Wilkinson Prize, Dolphus Prize, Whitehead Prize, and Crawford Prize, as well as some very distinguished talks at ICM. With that, I'll let him talk today.
Thank you. It's a real pleasure to be here. As you just heard, I used to work here. It's a pleasure to return. I've just spent 4 hours in the company of 12 ICME students, and it was just a wonderful time. Really impressive group of students, and really nice to hear about what's going on here. And I'm going to take my revenge and tell you now about what I'm doing. The subject at hand is graph-based learning. This is a smallish but important corner of the subject of machine learning. I want to, before launching into it, tell you what my perspective on the subject is and what I'm going to do for you in the talk and what I'm not going to do. This is not a talk about finding the next best algorithm. Primarily, I'm interested in understanding existing algorithms. And so I'll do two things in this talk at a high level. One is to look at a variety of different algorithms that are used in machine learning and in other areas of inverse problems, and unify them through a single perspective. And actually, the probabilistic way of looking at those algorithms will be very helpful in unifying them. So that's the first goal, is to unify a number of different algorithms. The second thing I'll do is look at a large data limit. Sorry, so the first part of that work is joint with Andrea Bertozzi and Michael Ruo from UCLA and Costa Sigilakis at Edinburgh. And there we go. And the second part of the work will be concerned with the large data limit of these machine learning algorithms. And this builds on work of Deanne Slepcher, who's at CMU, one of his postdocs, Matt Thorpe, and Matt Donlock, who's also at Caltech. So those are the two primary things I'll be doing. And in the second part of the talk, I'll be making connections between graph-based learning and optimization problems in differential equations, partial differential equations. Okay, so there's a number of papers I'm going to bring together in this first part of the talk. The first is an early paper in graph-based learning that came out of CMU. A number of papers published in this area, only available as CMU preprints. This particular paper is ICML 2003, and there's a number of papers around it, which I can tell you about, too, Garamani and Lafferty. And this is use of harmonic functions. The probit method, which I'll describe to you during the talk, and is described in a non-graph-based setting in this classic text of Rasmussen and Williams in Gaussian processes. There's work of Andrea Bertozzi and Adjuna Flenner using Ginzburg-Landau approach, which I'll briefly touch on. And then there's the level set method, which is a method from applied mathematics, which I'm going to link with the probit method and show you that they're very essentially the same method. So this is a method from physical-based applied math. This is a method from machine learning. And in this graph-based context, I'll show you they're essentially the same. The first part of the talk is already appeared on the archive. The second part of the talk, I'll make a link with partial differential equations by taking a large data limit, is based on a really nice paper of Deanne Slepcher and Nicola Garcia-Trios, which you can also find in the archive and recently appeared in ACHA. And then the work building on that is in progress and not yet complete. Okay, so depending on your perspective, I'm going to give you different ways of looking at the graph-based learning problem. One through optimization, one through probability. You may prefer one or the other, but I hope you will be open-minded to take in both of these perspectives and the connection between them. But in particular, the probabilistic uncertainty quantification perspective that I will give you is a unifying one. And So bear with me if that's not your normal way of thinking about these kind of problems. I will discuss some theoretical properties, algorithms, and then look at the large data limit, which, as I say, will connect with calculus of variation forms and in PDs. Okay. This is a problem statement, and I'm fond of saying at the moment that my own experience of going to talks is that I spend the whole hour working out what the guy said in the first couple of slides. And so to combat that, although it's not combated, you'll see why in a moment, I've written the problem statement on the whiteboard here. For those of you that have really good eyesight, you'll be able to know what I said in the first couple of slides. This is a re-summary of what's here. But let me just go through this carefully to make sure you take it in. This is a problem in what's known as semi-supervised learning, where the objective is to use what I've called here and what's traditionally called unlabeled data and combine it with labeled data to label the whole data set. So let me explain that a little bit more carefully. So the unlabeled data is n, capital N, vectors in Rd. So I'll call these xj. And these are characterized by indices j from the set z, which is just the integers from 1 up to n. And later we'll make a graph whose vertices are these points from 1 up to n. Then there is labeled data, so a subset of these points, z prime, which is a subset of these indices j, is labeled. And it's labeled, I'll just do binary classification, although that's not essential, but it's simple for presentation. So the labels will either be +1 or -1. And the objective is to use the correlation information in this unlabeled data to spread the labeling from z prime to the whole of z. Okay, so the output that we'd like are labels everywhere, on the assumption that we only have labels on a subset of the nodes, or we may have them everywhere, but they may be noisy. Okay, and that's this basic setup is written down over here. So this is the unlabeled data, xj, j in the subset in the set of integers z, and the labeled data yj in a subset z prime. So the optimization approach to this problem will be based around optimizing over W, which will be a real valued function defined on the graph nodes. And the graph nodes will be the set Z of points from 1 up to n, integers from 1 to n. We'll optimize with respect to this real valued function W, the sum of two terms, one of which is quadratic and will represent correlation information from the unlabeled data, and the second of which is will not be quadratic in general, and will represent the labeling and the constraint to be faithful to the labeling that is given to us on the subset Z prime or to the nodes Z. So roughly speaking, from an optimization perspective, these methods are a competition between a smoothness term, which reflects correlation in the unlabeled data, and a penalty term, which reflects the labels that we're given. And to be more specific, C inverse will either be the graph Laplacian, or it will be derived from the graph Laplacian. And the graph Laplacian will be computed in the way that I'll describe in a few moments, using the unlabeled data. So the objective here is to link this label, or a key point to understand is we're linking labels which are plus or minus 1 with a real valued variable W, which is the one that we'll be optimizing this with respect to. And the link between real values and labels plus or minus 1 will be through taking the sign function. And that, for those of you that come from a background in applied math or level set method, that taking the sign function is very much related to going from a level set function to a piecewise constant function whose interfaces are the objects of interest. Here the interfaces are between the labels plus 1 and minus 1. Okay, so any questions about the problem statement? But in general, I welcome questions. So I've been sampling the well-educated ICME students about how much they know about the graph Laplacian to determine how much time I should spend on this slide. They all know everything about it, so I'm not going to spend very long on this slide. But let me do it a little bit carefully. So just to remind you, I'm trying to explain where this quadratic penalty comes from. From the unlabeled data, I'm going to create edges on the graph whose vertices are the points from 1 up to n, where the unlabeled data lives. And the weights, roughly speaking, the weights are large between nodes which have a similar feature vector at each node, and small between nodes where the feature vector dxj is different at each node. And that's achieved through the 3 bullets at the bottom here. And then, then we get a weighted adjacency matrix on this graph. We can create a diagonal matrix by summing along rows, and then get what's known as the normalized graph Laplacian L, created in this fashion here. And throughout the talk, C, whose inverse appears in the quadratic form in the optimization problem, C will be, of this form, will be a linear combination of the graph Laplacian and the identity raised to some power. Okay, I'll show you in a moment that the clustering information is very sensitive to the edge weights and how they're computed from the unlabeled data, but that is not the thrust of this talk, but I do want to mention it because it's an important aspect of this problem area. Generally speaking, an interesting thing for me about this problem area is that it's an area where there's been a lot of what I would describe as engineering success, but there's very little theory. And for me as a mathematician, and for many of you, I think it presents a really good area for applied math. Because the problem areas of intrinsic interest, people need algorithms, but theoretical understanding is not needed. So just to give you, for those of you that have not seen it before, some insight into the properties of this Laplacian graph Laplacian, and in particular the normalized one, which I'm working with for the purposes of this talk, although everything I say works for the unnormalized Laplacian as well. And to establish notation. So this graph Laplacian has eigenvectors qj, eigenvalues lambda j, and here are 4 spectra computed for 4 different examples that will come up during the talk. MList, which is a digit data recognition. 2 moons is an artificial data set we'll see in a moment. Hyperspectra is a very large data set that I'll tell you about when we get there, where n is around 500,000. And a voting records example, which is nice to understand what's going on here. If we assume the graph is fully connected, which we will, lambda 1 is positive, lambda 0 is always 0, and that's because of the way L is constructed. And the fever vector is the eigenvector Q1 associated with the first positive eigenvalue. Okay, so why do we care about the fever vector? Just to build up information for those of you who have not seen this before. This is the voting records example from the US House of Representatives in 1984. There were here 16 key votes which characterize each individual, and these are the XJs, so it should be lowercase x. So those are sequences of 1s, -1s, and 0s, indicating voting yes, no, or to vote. So that provides correlation information between individuals. And in this artificial example, 5 of these individuals are labeled according to their party. So the +1, so this is a vector in RD, and there are labeling of 5 individuals, which are labeled according to whether they're Democrat or Republican. And here I've ordered the data so that the first, the ones to the left here are Democrats, and to the ones to the right are Republicans. And what I'm plotting here is the fever vector of that Laplacian, and what I would like you to see and take away from this slide is that the fever vector already does a pretty good job of partitioning the data into 2 groups. If I look at the sign of this function, of this vector, I would get most of the Democrats clustered here and most of the Republicans clustered here. So already this vector clusters. Okay? There's a lot more information in the Laplacian, and we will use it as we go on. But that's just to give you an idea that the leading eigenfunction has clustering information in it. The purpose of this slide, with a different data set, the two moons data set, is to show you that the way in which you construct the edge weights is important. This is an artificial data set, here shown in 2 dimensions. For the sake of the computation, it's embedded with the addition of random noise in 102 dimensions. These are the Fiedler vectors computed when I compute the edge function using here an L infinity norm and here an L2 norm. And what you see from this is that clustering is a lot sharper and easier if you use an infinity norm than L2 norm. That won't play a big part in this talk, but actually mathematics around how you choose the rate function and how that should scale with the dimension of the data, the size of the noise, etc. There's very little, and there's lots of engineering experience, and it's a good math problem. Okay, so now I'm going to tell you about a couple of optimization methods, and then I'll reformulate them in a probabilistic way in a moment. The first one is the probit method, which you can read about in Rasmussen and Williams, which is a classical text in machine learning. Although there it's not described in the graph-based context. But let me just show you that method in the graph-based context. There's a lot to take in here, and let me just summarize it in words before we go through the details. There are 2 terms. We're going to minimize this objective function jp over a real valued variable u. And based on what I've shown you in these examples, we can see that thresholding the real valued variable by its sign is related to clustering. I'm going to optimize this objective function and use the sign of u to cluster. Objective function has 2 parts, one of which, this quadratic form, roughly speaking, will has a tendency to force u to align with the Fiedler vector in rough terms, although it will align with other vectors depending on the second term, which sees the labeling. So what does this do? This, roughly speaking, forces u to agree with the sign of the label. So remember, the labels are plus minus 1. U is a real valued thing over which we're optimizing, a real valued vector on the graph. And if you look in detail at what phi p and psi do, they force you to agree with the sign of y. So let me just show you why that is. Psi here is the cumulative distribution function of a Gaussian with standard deviation gamma. If you think of gamma as being small, psi here then is evaluated at the product of y and u. So that means we evaluate it with v equal to the product of y and u. If u is small, psi will be approximately 1 if the sign of u agrees with, I don't know how I did that, and I'd never be able to repeat it. If the sign of u agrees with y, psi will be approximately 1, and if the sign of u disagrees with y, psi will be approximately 0. If psi is 1, then its log is 0, and you don't penalize. If psi is 0, which means that the sign of u disagrees with y, the log will be infinite, and this will be, well, it'll be minus infinity, and the penalty will be large. Okay, so this drives u to agree with the sign of the data, of the labeled data, plus or minus 1. Okay, a completely different method, so the level set method, for those of you that don't know, which may be small in number, but anyway, let me just assume there are some of you who don't know. Level set method has a long history. It was developed by Osher and Sethian in the 1980s as a way of describing interface problems via a continuous function which is thresholded to produce interfaces. It was subsequently used by Santosa to solve inverse problems for interfaces. And in a particular form that would be relevant here, we adapted it to a Bayesian formulation of inverse problems for interfaces. Here, the interface is the interface between labels plus 1 and minus 1, and it's an interface on the graph. And level set model works like this. We have the same quadratic penalty, which tends to favor aligning with the feedback vector. And we have a penalty term which penalizes the sign directly, penalizes the sign of u from being far from the labeled data y, which takes value either plus or minus 1. And so this looks directly like the way I was talking about probit model was in terms of the sign of u and how it aligns with y. In this model, we've directly built the sign of u in. Okay, so these are two different optimization methods, one coming from physical-based applied math, one from machine learning. Let me give you a way of thinking about both of them in a single probabilistic way, and then we'll take a minute where they simplify and where they relate to a method based on harmonic functions, or kriging, for those of you that know Bayesian process regression. So let me restate the problem in a Bayesian way. So this is exactly the same slide I gave you earlier for the problem statement, but I'm now going to view the unlabeled data as prior information through the graph of Laplacian and that we constructed from it. I view the labeled data as giving a likelihood, which will differ depending on whether we talk about probit or level set method. And what we would like is to label all of the points on the entire graph as plus or minus 1. So we'll in fact compute a posterior distribution on a real value function whose threshold will give the labels. So the connection between probability and optimization is the standard one, where I'm going to take the objective function that I described to you before and exponentiate its negative. And that will give me a probability. And I can reformulate that using this structuring the data into prior and likelihood as the product of the exponential of minus a penalty term, which is the likelihood, multiplied by prior information, which is Gaussian, and the Gaussian is a Gaussian with covariance C. And that covariance C contributes then to this quadratic form here, in terms of precision C inverse, and the likelihood contributes to creating this term here. So the two optimization problems I described can both be viewed as probability maximizers for this Bayesian formulation of the problem. And I want to get into a little bit more details to the underlying Gaussian and give you a bit more detail about the role of not only the feedback vector, but all of the eigenvectors of the graph Laplacian. So remember that the eigenvectors are Qj, the eigenvalues are Lj, lambda j. And the Gaussian that I've just described can be sampled by making a random linear combination of the eigenvectors of the graph Laplacian. So these are the Qj's. It's random because these Zj's are the N01 IID random variables. And then I'm going to weight them according to this function of the eigenvalues of L. So this function is just shift the lambda j's by constant and then raised to a negative power. This will tend to put weight on, and I'm starting this at 1, which means I'm excluding